Welcome back to Math 151. During class, we already saw how to use L'Hopital's rule to evaluate limits of certain indeterminate forms. But there's still some limits that we don't know how to compute. Consider the following. The first thing to convince yourself of is that this is not an obvious limit. If we use substitution, then as x is getting bigger and bigger, the base is getting closer and closer to 1, while the exponent is approaching infinity. We say that this limit is of the form 1 to the infinity, which is an exponential indeterminate form. Remember, indeterminate here means that we can have two things of this same form that give two different limits. You might be thinking, well, 1 raised to anything is 1, so this thing, 1 to the infinity, should be 1 also. But that doesn't work, because the base here is not literally 1, it's a number that's getting close to 1. So when we plug in some specific values of x, we can get a feeling for what's happening. When x equals 2, the base is 1.5, which is being squared to get 2.25. When x equals 10, the base is 1.1, which is being raised to the 10th power. That's approximately 2.5937. And finally, when x is 100, the base is 1.01, the exponent is 100, and this is approximately 2.7048. Numerically, it doesn't look like this limit is approaching 1. It seems to be growing as x grows, and we don't know what it's growing towards. Maybe it approaches 3, or maybe pi. Maybe it grows to infinity. Or maybe once x gets to be 1 billion, this number starts decreasing again. We don't know. The point is that it's not obvious, and we can't tell what happens without a new idea. The idea here is going to be to reduce problems like this to more familiar limits. And the way we're going to do that is by using logs. We're going to take advantage of the log rule that says a number raised to a power, when you take the log, that power comes outside and gives you a product. We start by setting y equal to the limit that we're interested in. And the question we have to answer is, what is y? To do that, we're going to use our idea of logs. So step 1 is going to be to rewrite the natural log of y. Now, we're taking the natural log of a limit. A natural log is a continuous function, so it acts nicely with limits, and we can rewrite this first as the limit of the natural log instead of the natural log of the limit. Now, inside the limit, we have this ln of something, and we can use log rules to reduce that. So we wind up with the limit of x times the natural log 1 plus 1 over x. In other words, our original exponent times the natural log of our original base. That was step 1. We just applied the natural log. Now in step 2, we're going to want to compute what that is. This limit is of the form infinity times 0. That's because when x gets big, the thing inside the natural log is getting closer and closer to 1, but the natural log of 1 equals 0. So this is an indeterminate form that we are already familiar with. And the strategy for figuring out a limit of this kind of form is to make this product into a quotient. The forms that allow you to use L'Hopital's rule directly are both quotients, 0 over 0 and infinity over infinity. So we're going to rewrite this. Instead of x times something, we're going to say that something divided by 1 over x. These are algebraically equivalent, but now this limit has the form 0 over 0. As x gets big, both the numerator and denominator are approaching 0. So that is a limit that we can apply L'Hopital's rule to directly. It's a good habit whenever you want to use L'Hopital's rule to first write the indeterminate form that allows you to do so, in this case, 0 over 0. And then to make some note that you're using it, my preferred method is to put a little LH above the equals sign here when I actually use it. That means taking the derivative of the function on top and taking the derivative of the function on the bottom separately, not using the quotient rule, but taking two unrelated derivatives. Here on the bottom, that's easier. We have 1 over x, also known as x to the minus 1. So we can use the power rule. That becomes minus x to the minus 2, or minus 1 over x squared. In the numerator, we have a composition, so we have to use the chain rule. On the outside, we have the natural log function. And when we take the derivative of the natural log function, we get 1 over whatever's inside. And then the chain rule says we have to multiply by the derivative of what's inside. The derivative of 1 plus 1 over x is also minus 1 over x squared. Well, we have the same thing on the bottom, so those two guys cancel out. And algebra just gives us the limit as x goes to infinity of 1 over 1 plus 1 over x. Now when x gets bigger and bigger, we see this is just approaching 1. So we know the natural log of y is 1. But the question we wanted to answer wasn't, what's ln y? The question was, what's y? We have to use the fact that e to the x and ln x are inverse functions. So y is e to the ln y. In other words, to compute y, you just take e and raise it to whatever power we got in step 2. So in this case, the limit that we started out with here, that equals e, which is approximately 2.718 yada yada yada. That looks more like what we were getting numerically on the previous computation. This limit is related to the problem of computing compound interest. Actually, this might be the way that you first learned about the number e in an earlier class. In the textbook, exercise 58 says, show that this related limit equals e to the r. So for any specific value of r, we have a limit here of the form 1 to the infinity. And if you choose r carefully, you can get a limit which is any positive number. For instance, say you want something whose limit equals 7. Then I would just look at this. So you can get any positive number this way. So this shows that 1 to the infinity is indeed indeterminate. And we will see during these videos that the 3 exponential indeterminate forms are 0 to the 0, 1 to the infinity, and infinity to the 0. And whenever you're confronted by a limit of one of these forms, you're going to want to carry out the same steps that we used here. So if we have a limit with some base function, bx, and some power function, px, then we're going to want to do the following. First, in step 1, we're going to want to use log rules and the fact that natural log is continuous to rewrite ln y as the limit of the power function times the natural log of the base function. Then, in step 2, you're going to want to compute that limit that gives you ln of y using the tools we already have, algebra, L'Hopital's rule. And finally, in step 3, you're going to compute y, our original target, by raising e to that power we got in step 2, raising e to the natural log of y. Please go on to the next video where we will practice using this method on more limits.